So we went back to the drawing board at that point and looked at what we could do to get away from the natural frequency problem, and that's when we went from a 3-bladed rotor to a 2-bladed rotor. And we also stiffened up the wing structure. The wings were soft, torsionally and bending-wise, so we stiffened those up with struts. So later pictures of the XV-3, you see struts on it and different rotor system. We then contacted NASA, and NASA Ames had just opened up their 40 by 80 wind tunnel, and we did some testing of the aircraft full scale in the NASA tunnel to determine whether or not we had solved the instability problem. So that's really where NASA came into it.
The second XV-3 accomplished the next major milestone in the program, a full conversion from helicopter to airplane mode and back. This took place on December 17, 1958, with pilot Bill Quinlan at the controls. In fact, this was the first complete conversion of any tilt rotor in history. The XV-3, although the first successful tilt rotor, wasn't the first designed. In the late 1930s and early 40s, England and Germany produced tilt rotor concepts on paper. In the U.S., one visionary designed a 53,000-pound model in 1946. None of these designs were built, but they were the first steps in the direction the tilt rotor would ultimately take. By 1958, of course, the XV-3 had the first tilt rotor conversion to its credit. It went on serving as a testbed until the program ended in 1966. During this time, it continued flight tests in both Fort Worth and at Edwards Air Force Base, California. From Edwards, the XV-3 went to the NASA Ames Research Center at Moffett Field Naval Air Station near San Jose. There it was used as a full-scale wind tunnel model to study the dynamics of wing and rotor interaction. Here, unfortunately, it met an untimely end.
We did follow-on studies, analytical studies on what the instabilities were caused, what caused the instabilities and how we could overcome them. We did some more wind tunnel testing, and ultimately, between NASA and Bell, we funded another wind tunnel entry into the tunnel at Ames with the full-scale XV-3, and that's when the aircraft came apart in the tunnel. We were testing. In the final phases of testing, we had proven pretty much the flight conditions, and we had proven that we had solved the wing rotor instability problem, but we had a mount failure in the tunnel. So the aircraft didn't fail, the mounting structure did, and as a result it blew down the tunnel.
In addition to its aeroelastic stability problems, the XV-3 was deficient in other areas too. For example, its performance was extremely limited. Unless the XV-3 carried minimum fuel and the outside air temperature was cool, the 450 horsepower Pratt & Whitney R985 radial engine could barely manage powering it through a vertical takeoff. Stall or short rolling takeoffs were far more common during the XV-3 program. The power-to-weight ratio of the R985 was not ideal for the tilt rotor concept. This problem was compounded by the fact that the aircraft was constructed with materials typical of the period. But the deficiencies of the two aircraft built and flown were not unique to tilt rotors. Instead, these were problems that the helicopter and aerospace industries in general were struggling to overcome. Despite its limitations, the XV-3, when compared to the pure helicopters of the late 50s and early 60s, more than doubled their 70 to 80 mile-an-hour top speeds. During the course of its 250 test flights, 110 conversions from helicopter to airplane and back, as well as 125 hours of flight time, the XV-3 proved the validity of the tilt rotor convertiplane concept. This was 1966. Ron Reber.
I think the XV-3 proved the concept of taking off vertically and then transitioning into airplane mode. We proved what Lichten had believed 10 years earlier, that it could be done and it was a viable concept. So the XV-3 showed that it could be done, and in fact it was a relatively stable aircraft. It was way ahead of its time, as it turned out. The difficulties that we had were not so much in the concept, but in the way that the aircraft was put together because of the technology that was available at the time.
By the late 1960s, two companies, Bell and another player, Boeing Vertol, were pursuing solutions to the tilt rotor puzzle on their own with additional funding from NASA, the Army, and the Air Force. Vertol, well known for their tandem rotor helicopter designs and originally founded by helicopter pioneer Frank Piasecki, switched their design emphasis from tilt wings and began a series of tilt rotor model tests, including 3,500 hours of wind tunnel time. As the 60s ended, Bell independently built a 9,000-pound full-scale tilt-rotor mock-up. This was their Model 300. This work in part led NASA and the Army to decide the XV-3's problems had been solved. Together, they funded another tilt-rotor proof-of-concept flight test program in 1972.
Then we went into a phase that NASA and the Army wanted to look at a follow-on program, an actual flight program. And we came up with the Model 300 and later the 301, which is the XV-15. We did some analytical studies and some more design concepts and looking at powertrains. And in '72, NASA had a proposal effort, request for proposals from the industry to actually build some more flying prototypes, proof of concept. We, Bell and Boeing Vertol, actually competed one against the other, and we were both in the middle of doing wind tunnel studies and our own analysis. Bell won out over Vertol and got the contract to build 2 flying prototypes. So that was the beginning of the XV-15.
Shorty Schroers describes the XV-15 and the tilt rotor concept.
Well, the tilt rotor is a novel type of aircraft that incorporates the low-speed capabilities of the helicopter, plus it can convert and fly as an airplane. Some people say you can't have the best of both worlds, but you can. Now, the XV-15 tilt rotor research aircraft has 2 rotors, one on each wingtip, which when in the vertical position can operate as a helicopter. And then on pilot command, the conversion can be placed, these pylons can be placed at any angle, so they are in effect speed control. The man can select the pylon angle and the fuselage angle that he wants and fly at that speed. So it gives the pilot a great deal of flexibility. And then it can go all the way to airplane mode, and then it's a twin-engine turboprop airplane. Now, it also is capable of going directly from helicopter to airplane mode. And it will do that in about 13 seconds. So you're accelerating from hover to 160 knots in 13 seconds. Pretty good kick. And the power plants for these 2 rotors, there's one on each wingtip, and they're basically the Huey Lycoming gas turbine engines. They've been modified slightly to run in the vertical position as well as in the horizontal position. And to protect the aircraft from an engine failure, they're cross-shafted together. So if you lose one engine, you keep both rotors turning. All the pilot sees is a loss in power, which he compensates for by pulling more power. The conversion process is done through screw jack actuators on the pylon, and they are also cross-shafted together, so that if you lose a hydraulic system, you can still convert. Each conversion actuator has its own hydraulic system, has its own electrical system. So you can suffer an electrical failure and a hydraulic failure and still convert. People always ask, what happens if you can't get them up? Well, my answer then is if you can't get them up, you're in trouble. But it's equivalent to not being able to get the landing gear down on a transport. It's about the same order of risk and complexity.
The XV-15 has been a remarkably reliable research aircraft. During its 5-year, 600-flight-hour career, the conversion system has never failed to safely function. To control a hybrid air vehicle like the tilt rotor, a hybrid flight control system is needed.